Okay, welcome everyone to this continuation of what is algebraic geometry. Today I would like to talk about finally the points at infinity. If you just really think about what projective geometry is all about, it's that those lines just meet at this point at infinity, right? And now I will try to make this really precise in the setting of algebraic varieties if you want. So what is the projective closure? And yeah, will be not big surprise hopefully at this point that projective closure adds these points at infinity at the same time makes something compact, but compact in the usual topology, not in the Zariski topology. But anyway, the starting point, historically, not the correct starting point probably, but for me, the starting point is the Riemann sphere, which I will call P for some reason that will become clear in a second. So for me, the Riemann sphere is this picture of a stereographical projection. So where here I have my complex plane, and this is a Riemann sphere, and you can go from one to the other by stereographical project, which I hopefully will just draw, which I will just draw in 2 dimensions. So in 2 dimensions, in this case, where you just choose a light source that's a north pole, and then this point here, the intersection is mapped to wherever it goes here. And when you can think of this is as soon as you go, sorry, this is bad, as soon as you go close here to some close point, it gets mapped to a very, very far away. And this gives you a projection between, well, essentially the plane and the sphere, just that the point itself is somewhere mapped to infinity if you just think of this type of picture. And yeah, if you do that on maps, so it will roughly look like this, which is somehow a bit distorted. So Greenland is kind of really tiny compared to Africa, for example. So that's why, so it kind of gets distorted towards the outside, and the North Pole is actually mapped to infinity. But the nice thing is that this guy, which I call projective one space, and this guy, which I call affine one space, so this one is compact, right? And the other one is not. And this is kind of the difference, if you want, between projective worlds and affine world. The affine world is really more like the usual plane, and the projective world is some compact object like a sphere. Okay, it's compact in the usual topology. Here I'm not doing anything fancy. It's really just compact in the sense of you can put it in a sack if you want. Right? So it's very bounded. Okay. And how does it work for projective varieties? Well, I have this picture. Here in this nice color, blue, I have the hyperbola, real pictures. The only thing I ever do are real pictures, of course. So x squared minus y squared minus 1 equals 0. Maybe I should have marked it like this. And you somehow want to specialize this little number here to 0. But of course, you can't really do that. There's no specialization. But anyway, the kind of thing here is this axis, x squared minus y squared equals 0. And how would you get this axis? As I said, you want to specialize to 0, but it doesn't really make sense. What would you specialize to 0? A scalar specialized to 0? The way to do this, and we had that in previous videos, is to add this time coordinate to make it homogeneous. And we're immediately in, so this is the blue one here. This is cone type picture. We are immediately in projective world. And now it makes sense to specialize z to 0, right? Specialize z to 0, you get exactly this equation, and the corresponding equation here in 3 space is still this cross times the interval, time interval, and it kind of lies exactly at the border of this funny double cone, right? So these guys somewhat touch at infinity if you want, because the hyperbola is somewhere here in this picture, and if you just draw that out, they kind of touch and infinity. And that's what I would think of closing something. You specialize to 0, but you're not really allowed to do it. So you add an extra variable that you then specialize to 0. Hopefully that makes some sense. You make it homogeneous by adding this extra variable, and then you can specialize that variable to 0, and that's somewhere where you see the points at infinity. If you're confused now, where are the points at infinity? You have this funny red line. Well, remember that in projective land, everything is just defined up to a scalar, and the line actually is a point. So here my point AA here is at 1, 1, but it's also at -1, -1, so 1, 1, -1, -1. So this whole line where A lies on is actually just one point in projective length, and it's a point at infinity, right? And similarly, the B, which is something like minus 1, 1, and at the same time, because you can just scale by minus 1, it's a point down here, and actually everything on the B line is just one point, which you can think of as the point at infinity. And this is why I would like to think of the cross, which is a specialization z to 0, as kind of adding the points at infinity. Right? And then you just say, okay, the point B is somewhere here, and at the same time it's somewhere here, and the point A is somewhere here, and at the same time it's somewhere here. So you added 2 points to infinity, and you get this the projective variety, which now has added the points to infinity. So let me run through this again. Make it homogeneous, specialize to 0. The new points you pick up are the points at infinity. I'll give you one more example. But here's a formal statement. So projective closure V bar of an affine variety. And I just stated for an affine variety generated by one polynomial. Something similar works for if you have more polynomials. But anyway, if that one polynomial is just there, you just make it homogeneous. I just showed you an example how to do it. And then the variety associated to it is this projective variety in the new coordinates. So f is a polynomial with one more variable, x0, and this one was just a regular one, and the points at x0 equals infinity, so x0 equals 0 are those additional points at infinity. Now it's this is called the projective closure, and now it sits in a compact space, so it's actually a closed set in that compact space, so it's compact in the usual topology, and it's a closure in the usual sense of the words. It's like it's the smallest thing that satisfies those conditions. So let's run it again just to be sure. So you take your polynomial x squared minus, oh, I actually have an extra example, so let's do it in here. You take your polynomial, whatever it is, it's not homogeneous, and it's a blue thing up here, right? It has those 3 type of branches somewhere. You make it homogeneous, like just add, in this case, this extra variable, and now you can specialize the z variable to 0, and you get this new equation, which is now the red thing, the red beast up here. Yeah, so this is this guy here, this triple whatever it is, triple 6 valid vertex or something. And then you can see the points at infinity, because again it's identifying along the line by the same thing that projective geometry always identifies along the line. So this whole line here, yeah, will be one point that you can think of as sitting here at infinity if you want, the point A. This whole line here is an extra point which kind of sits down here, the point B. And do I have an extra color? Maybe something like light blue. Yeah, let's see, that works actually really well. There's an extra point here which sits somewhere at infinity, and now the affine, so the affine variety is a blue thing, and the projective variety, the closure of it, is a projective variety which you get by adding the red thing in terms of well, projective space. So you add those corresponding points at infinity, and I just wrote them down in coordinates for you because why not? So you can double check. Hopefully I haven't messed up my coordinates. And this is kind of what you run in general. So take your polynomial, make it homogeneous, and yeah, specialize to 0 the extra coordinate. These are the points at infinity. And the new thing is now lives now in a closed space. In a compact space. So it's compact, and then you can show all the nice facts about it, like there will be some nice intersections or whatever. But I really like this picture of, well, you have the Riemann sphere, and really it just adds this point at infinity, and it really just comes from adding an extra time coordinate, and the time coordinate, when you specialize the time coordinate to 0, which you can't do for the original variety, you get kind of new points that come up as this specialization at 0, and those new points are those famous, I can't tell. Are they famous? Are they infamous? I certainly can't tell. Those funny points at infinity. And this is how we go to the closure, the projective closure of a variety. And yeah, we have now a compact object, which is really what you wanted to do. And in general, you might ask, well, if you don't have one polynomial but multiple polynomials, there's a similar procedure, which I decided not to bring up because I'm just too lazy. It's not difficult, but it's not as easy as just taking the generators of the ideal and make them homogeneous. It's a bit more difficult. Anyway, I hope you enjoyed this video, and I also hope to see you next time.